Good morning. Nice to see a few of you made it to come here in person to the classroom, and quite a few are online. We continue with the machine learning pipeline where we stopped, I don't know, 2 weeks ago, 3 weeks ago. And yesterday I sent this message and asked you, please have a look at this again, read the news article, think about how suitable this is for a machine learning task if you want to predict if you want to predict that a cat would survive or not. What are the challenges? How well does the model possibly work? I hope you all did this. So I'm going to ask you, so on the next, okay, let's do the Mentimeter first. On the next slide. So I hope you have read this article. What do you think? Let's go. Go to menti.com, type in this code. Okay, so you all choose mediocre because it's in the middle, so you can't be too far off the right answer. Do you want to explain why do you think it's average? Someone has raised their hand. Yeah, just turn on audio and talk.
Yeah. So I would have gone with an average due to the fact that we barely would have any extreme data for the top floors and the bottom floors for the cats. And with only having one success, it would probably assume, oh, everything above 32 stories would also automatically be safe. So it wouldn't be too reliable, but it could be somewhat reliable around the middle floors.
Okay, good. Any other opinions? The student said that there are no extreme values in the data that could make it difficult to make predictions, I believe, for the higher floors, if I understood this correctly. Yeah?
This would be difficult because such extreme environments the assumption that every cat has all Falschinterpretationsfähigkeiten. Dass man einfach sagt, dass es wirklich deswegen gleich ist. Oder mal hat so viel Gleiche, das sind halt wahrscheinlich kleine Werte, die viel ausmachen.
Okay. So you think we would need more data, like how big is the cat, how often does it turn around? Okay, so it's not enough information in the text. Should be more specific. Any other ideas, opinions? Okay, so my opinion, I mean, we never know for 100% sure until we really try it. But my opinion is, I can click and then there's no correct answer here. In my opinion, it would not work at all. So maybe think about this for 1 or 2 minutes, why I believe this. Maybe you change your opinion. Then I explain why I believe it would not work at all. I think the data is not suitable at all to predict if a cat is surviving or not once it falls down. Just go back to the text. Yeah. No.
So
not just not enough information. What cats are included in this data? Yep. Yeah, at a more higher level, what kind of cats are included in the study? Cats that are being brought to the hospital, right? What kind of cats are being brought to the hospital? If a cat falls down from the 30th floor and it's just mashed potato after that, you think the owner scratched together all these parts and brings it to the hospital? Yeah. Exactly. Exactly. Only cats are included here that where the owner believes there's a chance that the cat will survive. Possibly so maybe the cat is still alive once it falls on the ground and the owner sees the cat is still breathing and they bring it to the hospital. Some cats might die on the way. Maybe the cat is even dead when it falls down. The owner is just like hoping for a miracle. But still, there will be a bias towards cats that are still alive and have a chance of surviving. And that's a real problem that you will see in machine learning. I mean, this was not, I mean, this is not data really designed for machine learning, but you see this was published in the New York Times, one of the most apparently reputable. One second, my speaker. One of the most prestigious newspapers in the world. And what the scientist here is concluding is just complete nonsense, that the cats survive because they are like a flying squirrel or something. Of course, it may be that a cat has a higher chance of survival because maybe they stretch their legs and then it's like a flying squirrel, but the data does not support that. So it's like you just cannot make any conclusion if this data really can predict the survival rate. And this is something it's hard to teach how to see that. This is probably practice and critical thinking, that you don't take what someone presents to you as granted, but you really like try to go one step back and think about, is this data really suitable? And in my opinion, it's quite an embarrassment to publish something like this in a newspaper. And you will see that very often in newspapers, that the journalists are just very poorly educated. They can't identify that. And it's kind of quite embarrassing that the researcher is publishing something like this. But that happens. So it's important that you are more careful. I always get the message here that my speaker can't connect. So I hope, one second. Try to. Yeah. But then again, if you work in a company and you have a normal business problem, you will also run into problems like this. You want to predict something and you think, oh, I have this data, but it will be biased. Okay. Kind of new topic now. Some of you might have, who of you had a statistics class before? Or where you learned something about distributions? Yeah, you? Not everyone. You might have heard of a normal distribution, bell curve, something like this. And it's surprisingly often you see something like this when you measure something, when you measure the IQ of persons, the height of persons. If you repeat the same experiments, you do not always get exactly the same results, but you will have a normal distribution. And when you train a machine learning model, you will have also the same. So what you will see if you measure the IQ of people, it will be distributed like this. Over the whole population, the IQ is 100, the average IQ is 100. And then that is like most people, but have an average IQ, and you see then that less and less and less and less people have a high IQ, so a relatively small number has an IQ over 145 or below 55. Like 68% are in this orange area normally. That's called a normal distribution. It's just the same. So here's the number of standard deviations. So if you calculate the standard deviation, you can expect that between -1 and +2, you have 68% of the data here. 15 plus 15 plus this should be 68. Give me 1 second. I think there was... Right. If you remember, before we were talking about the cats, we were talking about outlier detection. And I showed you these examples. What is an outlier? Is that an outlier? And we said, oh, yeah, probably based on our, let me just go back. Is that an outlier or is this an outlier? How can you really determine this? I think here it's quite obvious if you look at it. Here, I don't know, maybe most of you would say, yeah, that's an outlier, but maybe 1 or 2 of you would disagree. And then the question is, who's right? How can you calculate this? So, sorry, all the jumping. So the normal distribution curve helps you, among others, to identify outliers, to say what is normal and what is not normal, what is beyond the expectation. And there's a few formulas you should know. But obviously, you know the mean, that's the arithmetic average. Then the variance, standard deviation, and the standard error of the mean. I explain some of that on the next slides. A normal distribution does not always have to be exactly like I showed you. It can be more skewed or more stretched. But always you have like typically the peak somewhere, and then to the left and the right, it goes up and down. Oh, WebEx really sucks. And there's lots of other distributions. We are not covering them. You should be aware that there are other distributions. And when you look at nature, when you measure something, you will often find something like this. One important one, where is it here? The long tail. It's not even in here, but on the next slide. A long tail distribution occurs in e-commerce, for instance. Often a few products make the largest percentage of your revenue, or here, if you look at the distribution of large cities, you will find that there's a few really big cities, just looking at the US here, but the same is true for pretty much every country in the world and the whole world as well. There's a few really big cities, and like if you would draw a line here, it will fall down very quickly, and then you have a long tail here where the numbers are quite similar. That's the cities you have never heard of. And the same is true for many things, products in a store, in terms of how much revenue they generate, how many views a movie accumulates. So some movies are blockbusters. They have on YouTube, they have millions or even billions of views. And then there's, of course, a very large number with very few views. What is the normal distribution here? This shows you an experiment. I believe I have shown that chart to you before. That was showing the model complexity. So how many degrees of freedom do you have in a model? That is here. So the independent variable, here you have well, and here's the prediction error. And each line here, each light line is one experiment, and then the bold line is just the average. So if you look at these experiments, where can you like explain to me where's the normal distribution here in the chart? Yep. The thick line, die dicke Linie? No. Like a normal distribution is like this curve. Where do you have this curve? Yep. Sorry? Where the most data appears? No. Let's give me some more information. So if you were to the context we're talking about here is about repeating experiments, and if something, an experiment, an outlier, is expected or not. If you see here, just any random point on the bold red line, if you pick any point here, let's say you were to repeat the experiment, you are conducting the same experiments and take a degree of freedom of 13. What is your most likely outcome? This one, right? If you had to make a guess before you run the experiment, what your prediction error will be, your best guess would be here the dot, the average of all the experiments previously conducted. What if you run the experiment a single time and you would get this as an output? Would you be surprised? Probably not so much, right? If you get this as an output, would you be surprised? Maybe, right? Or in other words, how likely is it that you get, if you run it a single time, this line? It's definitely less likely than getting this or somewhere here. So the normal distribution is this way. Yeah. The bold line is the average. That is basically, if you just go back here, that is basically here. And it's quite likely that if you repeat this experiment, you somewhere get a result in this area. It's not impossible, but quite unlikely you get a result here. You could call this an outlier. I mean, it's real, yeah? Same with the temperature. It's a real correct measurement. It's a correct outcome of an experiment, but it's just very unfortunate because it's quite unlikely to really give you a good estimate of the performance in the future. Very likely your performance will be here. So what is an outlier here? If you know that this is the normal distribution for the IQ in the population, is this an outlier? Is this an outlier? Or this? Or this? Or this? No? Yeah, it depends. Of course, it depends on, there's no right answer here. But at least we can define something. We can make a decision what we want to consider an outlier. There's no right or wrong here. So often something that is further away than a standard deviation of 3 is considered an outlier. Or actually, talk about that maybe later again, or you will see that in research papers a lot, confidence intervals. Sorry, this is not the standard deviation. This is Z. And that is a number, sorry, yeah, it's too early still. It's a number of standard deviations. So Of course, this would not be an outlier. That is the average. This is one standard deviation away. This is two standard deviations away. So I said before, in this area, you have 68%. In this area, you have 68%. Here you have 95, if I'm not mistaken. And beyond here, it would be even lower. But again, there's no right or wrong. You could also say that everything here is an outlier, everything beyond here. And there is different methods to explicitly calculate that. One is the box plot method. It's a little bit more complicated than just looking at the standard deviations. So in the box plot method, you have seen a box plot, I assume. It's quite a nice way of presenting distributions, better than just the average or the min and max values. So ignore the numbers for now. Just look at the box plot. Often the box plot is actually like this way. So the box plot tells you the median, so the value in the middle. It tells you the maximum value and the minimum value. Or there's different ways of presenting that. Sometimes it's not the minimum value and the maximum value, but something else. Then you have a sub-median. So you take basically this half from here to here. Look, where's the middle? That's the sub-median here. And the same here. So you take all the data from here to here and take the middle value that would be here. So in this example, you have the numbers 2, 4, 4, 6. So imagine these are the outcomes of your experiments or temperature measurements, something like this. So 2, 4, 4, 6, 7, 7, 8, 10, 13, 13, 14, 20, and 28. And you want to know which of these numbers are outliers. So again, assume it's an experiment, the outcome, it's the error rate. And then you calculate the average, the median, that would be the 8. So if your median outcome is 8, would 28 be a surprising number? Yeah, you don't need to calculate that, right? You would be very surprised if you say the average or the median is 8. Let's say the median income is 8,000 or 80,000 euros, and then someone has 28,000 or 280,000. That would be a much larger number. To identify the outliers, you calculate the interquartile range. So that's then actually here and here. And you calculate that by subtracting the two submedians, so Q3 minus Q1. And the example that is so 5 and 13.5. And then you calculate Q3 plus 1.5 times the interquartile range. So Q3 was what? Let's start here. 13 plus, I wrote it here somewhere. So here it's Q1, that is 5 minus 1.5 times interquartile range. It's minus 7.75. Yeah, that is here and then here. And by definition, everything beyond here is considered an outlier. Again, it's just a definition. I mean, instead of 1.5, you could also say, oh, but I want 1 or 2. Or you could calculate the interquartile range differently, whatever. But that's just one way of doing it. Yeah, there's many ways of plotting box plots. Actually, this one is the one I like most, and it's probably also most common. But in the exam, if you're supposed to paint a box plot, please use this main one that I used here. But still, you should know this, so because the visualization is a bit nicer. Here, you don't draw like this line at the min or max point, like here in the chart before, but you draw there where the outliers start. So every dot beyond here is an outlier, and then you can plot the outliers as bold dots. It's much nicer to visualize. Yeah, and there's many, many methods, more which we will not cover. There's a good chance this comes in the exam. Every second year or so, I have that in the exam. Yeah, many ways more to calculate outliers. Pretty much every machine learning library has some tools to detect outliers. So you don't need to calculate it by hand. You just call the function in scikit-learn. So do that in one of the next lab sessions. Would be good practice. So what do you do with outliers? Any ideas? No. So delete from the data set. Yeah, that's one option. Anything else? I think I showed that to you already in one of the previous slides. Or not. But anyway, what can you do with outliers? Delete. Yeah. Give them less weight, depending on what you do. Maybe you can give less weight to them. Yeah. Something else? Change the value, like change the data, make it smaller. Could that make sense? Yeah. Take the log of the whole data set. Yeah, so you would not just treat one outlier, you would treat the whole data. You can do that if you take the log value of every entry in your data set, you will have less outliers. And it's like if you take the logarithm, it has a stronger effect on large numbers than on small numbers. So it's basically skewed together, kind of. And that can be extremely effective sometimes. That is absolutely right. These are some of the things you can do. Like one of you said already, remove them. Then another simple method is Winsorizing. So you cap them at the threshold. To do that, you decide on a top and bottom threshold. So you kind of say, okay, we take the top 5 values and the bottom 5% of the data. That gives us like a 90% Winsorization window. And you replace the values at the bottom or the top with a threshold value. So let's say these are the original numbers that you have, starting from 0.1 over 1 and 12 and 14 up to 99 and 125. You decide on a 10% threshold on each side. That means so it's 20 numbers. So 2 numbers in the top and 2 numbers in the bottom, you just replace with the, let's call it the first valid value, so 12. And then your data becomes 12, 12, 12. And here, this 44 remains, and then you replace the 2 large values by 44 and 44. Or, like what you just said, you transform your whole data, you take the logarithm, you normalize it or you standardize it. You can build bins and things like this. And I think I've showed to you on the previous slide that there's, again, not the one right answer what to do with it. It's not, the effectiveness can be different. Sometimes Winsorizing is most effective, sometimes logarithm is most effective, sometimes removing them is most effective, and sometimes not doing anything at all is most effective. Actually, that's something I should put on the slide. Do nothing. That's absolutely also a valid option. A really annoying thing if you work with real data is missing data. You will, if you work in a company, you will always stumble up on this problem that you have missing data. And then sometimes it's not even missing data, but just like incorrectly formatted data. So like you have some other data inside, or it's just missing. Any ideas why data could be missing? What are the possible reasons? Yeah. Sorry? Mm-hmm. Yeah, if you have a survey, the person might have, same in an online form, the person might just not have given the data. That's maybe the most common reason. Yeah. Any other reasons? Someone might have accidentally deleted the data in a company. That may happen. Or when you are writing the data or copying the data from one place to another, sometimes there's problems there. There's, yeah. Yeah, if you connection errors when you write to a database or when you transfer data from one place to another. If you work in a company, you have one large database and you're maybe, what's the English word for that? In German, Migration, ne? Von einer Datenbank auf die andere migrieren. So if you change the technology, you go from MySQL to some other database technology and you copy all the data from one database to another. Maybe you forget some data to copy, or it's not compatible, whatever. There's a classification of the type of data that can be missing. It could be, and it's a bit weird, the naming you will see in a second. So for the reasons why data is missing and why people maybe do not give answers. The first one is missing completely at random. So there's no real reason why something is missing, it's just random. If you send, and even actually the example here, I would argue it's not entirely random. So the example here on the slide is that you do a survey and the data is, the survey is lost in the mail. Is that really random? Do you think if you send 1 million letters all over from Germany or different parts of the world, maybe even, that, and then you will find out 1% of your data is missing, 1% of the, more realistically, probably 0.1% of the letters went missing? Is that really entirely randomly? Yeah. No. Let's assume they filled out the survey and you are sending it, they or you are sending it by mail, and the mail, the post office is losing it, delivering it to a wrong address or whatever the reasons are that mail doesn't arrive. Is that completely random? Post office with some mistake, like in specific. So most of the people like around this location will probably be missing in the data set. Yeah, but could there be a reason why one post office is more likely to not deliver the mail than another? Yes, what could the reasons be? Yeah, so I can also only speculate, but my assumption would be that the further away a post office is, the more likely the mail get lost. I think if you send a letter from China to here, it's more likely to get lost than if someone sends a letter from Cologne to here, because from Cologne to here, it's just basically one step. You bring it to the, well, actually, no, it's not one step. You bring it to the post office brings it to the central distribution center, and from there it goes to to Düsseldorf or to Siegen or wherever to the next step. If you send a letter from China or India or somewhere, you will have many steps in between, and at every step in between, there's some chance the mail gets lost. Maybe the post office burns down. I would assume that in areas that are more poor, chances are higher that mail gets lost. Maybe the post office is robbed or something like this. Anyway, there's a category called missing completely at random. Then there's a category called missing, and I don't know why they call this completely at random and this missing at random. So this one is a much better naming, missing conditionally at random. What you see here is that if you have missing values, they often correlate with another variable. If you collect IQ values, so self-reported IQ values, then older people tend to report them less often than younger people. So if you have missing values about IQ, you can make the assumption that there's a certain chance that person is relatively old. Of course, there's no guarantee, but there's a correlation between it. And then you have data missing not at random at all. There, the missing value relates to itself. And I think with IQ, that's a very plausible explanation. People with a low IQ, if they know they have a low IQ, they are less likely to report the IQ in a form, in an online form. Nobody wants to admit that they are not the brightest. So if you have a database and you have data about certain persons and their IQ values, and the IQ value is missing, there's a tendency that these persons are either older and or have a lower IQ value. And this is true for many, many things. Is missing data bad? Why do you not just ignore it, or like, what's the problem with missing data? Let's go one step back. What's the problem with outliers, potentially, for machine learning? Why are outliers potentially bad? Not always, but often. Yeah. Yeah. So an outlier potentially is biasing your model. Think of linear regression. You want to have a straight line or a linear model that models all your data points as good as possible, and actually not your existing data points, but your future data points. If you have one out, so if your model looks like this, and there's an outlier included, and without the outlier, the model looks like this, then this model is more likely to be suitable for future unseen data than the model that includes the outlier, because an outlier is just an outlier and hopefully not occurring too often. Now back to missing data. What's bad about missing data? If you want to do KNN or linear regression, what do you do if a feature is missing? Why is it? Or is it not bad? I mean, with outliers, you can just do nothing. And there's a good chance that your model is not so strongly affected. How about missing values? Can you also just do nothing? No, at least for the models we are talking about, you must do something. Think of linear regression. What do you do if a value is missing? You can't. I mean, linear regression is a function, it's a formula where you must have your x1, x2, x3, and the weights. What if x4 is missing? you cannot put a null. So it's like the data type. I'm not meaning a 0. I mean the null value. You cannot put that in a mathematical function. It's not defined. You could use 0. You could, but that's not the same. If you use a 0, that means you have substituted the missing value with a 0. So you must, with most machine learning models, you must do something. And again, machine learning libraries have plenty of features what you can do. So what you could do is either delete the entire instance. You have a question? Yeah, that's one solution. Yeah, so that's what's here on the slide now. You can interpolate sometimes if it's some time series data. So if a data point is missing, you take the data from before and the data from after that and substitute that. Or you delete the entire instance. If you have a large data set and only few data is missing, it doesn't matter if you remove 1% or 5% of your data. But if that's not the case, there's other options. You could encode the data as missing. So that means you replace this missing null value with some information that is otherwise not being used. So if all your data for the if all your existing data, let's say, are positive integer numbers, you could encode the missing value as a -1, maybe. So that the machine learning model has a chance to learn, okay, there was something different compared to all the other values. Or you just replace the data with the mean or median or modal value. And of course, you could predict the missing value with machine learning. That adds a lot of complexity, but might work very well. Talk a little bit about visualization now. How can you visualize the data to see some patterns? Bar chart, every one of you have seen that in newspaper articles, in research papers. If you do homeworks, you probably use that a lot. So you can use that to visualize how many features, how many instances in a data set have that feature. And if you would see that a large number of instances does not have this feature at all, maybe you can also just remove the feature entirely. So you're not using it for machine learning. I mean, what you see is the count of missing values. So you're not looking at this, but rather at this. So if a large number of instances has missing, if one feature is often missing, you remove that feature at all. There's correlation heat maps. I believe I showed that to you as well already. Yeah, you just have all the features and their correlation with all the other features. And so this is not just about missing values now, this is in general about visualization. Then you can use this to, again, identify features that you maybe don't need or that are particularly important. This one you don't need to memorize or to learn for the exam. It's just for you later. If you really work with data, maybe in the lab sessions, have a look at this to decide what to do with missing data. Right. This is an experiment that shows you how effective the different methods are for treating missing values. So the researchers here compared to impute the missing values, they used the mean, they used K and N. So they just took, as a replacement for this missing feature, they just took that value that the K nearest neighbors had. The K nearest neighbors defined by all the other features. FKM, I forgot what that stands for. SVD, singular value decomposition. So this is kind of machine learning algorithms. Then there's two different data sets. The IRIS data set, it's like a very small standard toy data set for machine learning, and the E. coli data set, it's the same. Let's have a look. It's a while ago that I looked at that. So we ignore these metrics because we have not covered them. We look at RMSE, and you see here that this blue-green crosses are worst. So they have a high RMSE. Which one is that? It's a bit difficult to see. So what I would take from this is that here and here, the results are relatively similar. So it appears to me that the worst algorithm here is also the worst here. And the best one appears to be this green and yellow line, which is probably this and this. So that appears to be some machine learning algorithms that are being used to impute the missing values. Missing data is not new. Statisticians have dealt with this long before there was machine learning. There's thousands of research papers on that and how to treat that. And if you look for just for handling missing data, which is already a very specific search term, you get 17,000 research papers on Google Scholar. So people have published 17,000 documents about how to treat missing values. If you want to read all of them, you probably are in retirement age by the time you're finished. A really annoying thing is inconsistent data, and that happens a lot as well if you work with real data. And I mean, you see all these things that can happen, outliers, missing values, and we are not finished by far. There's much more coming. Inconsistent data. I often get emails from students who want, is the camera still following me? I often get emails from students who want to do their bachelor or master thesis in a company. And they asked me to supervise that. And I'm not very happy about this because most of the time these projects are very boring for everyone because the students will end up probably not, I'm not sure if it's 90%, but a large portion of their time doing all these things, cleaning the data, looking for missing values, thinking about how can they impute this. They do something, it's not working. Then they look at the data, they maybe find some problems like I'm explaining in a second, and they only work on cleaning the data for a long time, and they do not do anything really interesting and productive. So inconsistent data. That can happen either if different programs write in the same database and the programmers did not talk to each other, or if over time the programmers change just the syntax for the database. If you look at an example, this is a made-up example, but there's many ways of encoding gender. You can use numbers, 1 or 2, or 0 and 1. You can use letters. You can write this. And in this example, it's just 2 genders. So if there's more genders, then this becomes even more error-prone. And imagine, I mean, for your machine learning algorithm, it's important that this is well encoded. Because otherwise, in this example, like if you would do everything automatically, here you would end up with 3 different encodings, right? So you would have, your machine learning algorithm would learn that there are 6 different genders here. Although, at least in this data, it's only 2. So that's not what you want. This potentially will decrease the effectiveness of your machine learning algorithm. And this can, of course, not only happen for gender, but for every variable. Sometimes the year of birth is stored as text. Sometimes it's a number. Sometimes it's a 4-digit format. Sometimes only 2 digits. So ideally, you would look at every column, at every feature, get a list of all unique values, and then you look at it and you say, that looks good. Or that's not good looking. Here, something is wrong. We should fix that. It's not a problem if you have just 4 features, you can do that. But if you have 1,000 features and maybe not so obvious right and wrong values, you can spend days doing that. Yeah. Has any one of you ever worked in a company and experienced something like this? Yeah, I see 2. And was it, can you tell us a little bit about it? Was it a big problem, really annoying, or just like very quick and easy? Yeah. So how long did it take you and how big was the data set? Mm-hmm. Okay.
Some data were put from an app, and some data were put from forms from an online form. Like
mm-hmm. Yeah.
Yeah. So some columns were like the bird here, your bird was quite the same.
Yeah. Yeah, that's another really horrible issue that's not on the slide. Encoding in general, you know, if you use UTF-8 versus some other encoding scheme, and then umlaut, German umlauts are sometimes written wrongly, and then you have basically maybe city names. It's the same city name, but in the database it looks like 2 different cities. But what you said, like 4 to 6 hours, that's a lot of time for a 2,000 row data set. I mean, imagine you have 20,000 or 2 million. You mean rows, like instances, or you mean features? Rows. And how many features do you remember? Okay, so that's a tiny data set. 2,000 instances and 10 or 12 features. That's like nothing. And still it took you 4 or 6 hours. Yeah. Yes, but if you don't know how maybe to make it more efficient, then, I mean, yeah. Or, yeah, duplicates. I don't have any text on the slide because I just added the slide. But you will, let me think of an example. Yeah. I think I mentioned that before. I once developed a recommender system as a service. So companies were sending requests to my API that they wanted product recommendations for a product that a customer was currently looking at on their website. And we did that, and then we were logging clicks so that we could later see, okay, user clicked on the recommendations. We delivered 10 recommendations, and when a user clicked on 1 or 2 or 3 of them, we were writing this click to our database with a timestamp, referring to which recommendation was clicked, and some statistical information of the browser and so on. Now the problem occurred when a user clicked 2 times on the same recommendation. Then we ended up with 2 log entries. They were identical, but only the timestamp was different. That's not really a major problem, but you need to think of it. We did not think of this in the beginning. And then when we did our analysis, we thought, oh, so many, like a relatively high number of clicks because we counted those 2 clicks twice. And then we fixed that. And only later we realized that also some of the other variables that we were logging, I don't remember what, but something, you know, you can, via JavaScript, you can log a lot of information about a user, the operating system, the browser version, the browser name, which plugins they've installed and other things. And some of these features also changed. So it took us some time to identify that. And there's many examples more where you will end up with two instances that basically are the same, but they make 2 or 3 or 4 instances in your data set. Yeah. Important is also feature engineering. You can often not just take the features as they are, you must do something with them. Let's look at some examples. Now, what do you do with this? If you have, so what do you do with this? If you have linear regression. Yeah. That's correct. Keep in mind, first of all, for linear regression, you can never ever work with null values, and you always must have numeric values. You cannot work with categorical values. So it's impossible. You cannot put the letters MALE in here. It must be a number. It can be any number. Positive, negative, decimal, integer. So how do you do that? How would you transform these features into numbers? Yeah. Okay, we could take 0, 1, and in this case here, 3. We have 3 genders here. 1, 2, 3. Okay, we could do that. So then there's, again, different options. What do you think is better? This one or this one? 1 second. Here, let's use a Menti again. Okay, those who chose the first one, just keep one column. What do you think is the advantage over having multiple columns? So going back here, what's the advantage of this over this? Yep. It's less complex, like you have just one column, right? Because otherwise, if you do this for all your features, and if you do not just have like 3 here, but like some feature with maybe 10, 20, or 100 values, you won't end up with a very large table. Yes. Is there any disadvantage of the one single column solution? Yep. Okay, that's a good point, actually, that if you have this, you don't know anymore what it means. Some new person would not understand that, but actually that's not important for machine learning. We are not talking about changing this in the database, for instance, but just doing it in memory or just converting it for training your machine learning model. So, but in general, of course, that's a valid point. if you think about how to store it in a database, here the new software engineer looks at it and knows what it is. And here, of course, you need some documentation. That's that. Yeah. Normally, your software engineers who maintain the database will not be happy if the machine learning engineers come and says, but for me, it would be easier if you store all the data differently and you convert all the data in your database. It's typically better if you just take what the database people give you and convert it, but yes? Yeah. Yeah. Yes, exactly. That could be a problem, and not just with gender, with every feature. If you have numbers 1, 2, 3, 4, 5, 6, there's a natural inherent ranking included. 6 is 6 times as large as a 1. Before that, here and all categorical features, there's no inherent value or ranking. So if you do this, I mean, you could do this, but chances are high your learning will not be ideal. So what is normally being done with algorithms like linear regression, not with all algorithms, there are some that can even work with this. But with algorithms like linear regression, what you typically do is this. So indeed, your table becomes very large. And by the way, that's also a reason, like, you would never, ever save your data in a database like this. If you attended, well, okay, I'm not a database expert, but I'm pretty sure that most database people would say, oh no, I mean, for 3 features maybe, but not if you can have 1,000 potential values. You would not have 1,000 columns in a database, and it's all filled with zeros. That's a huge waste of storage. But for machine learning, this is what you need for linear regression, at least. So you are transforming your features into this binary representation where every potential value in here becomes a feature. And then only the feature that is actually given becomes a 1. So here, male is a 1. Female is a 1. Diverse is a 1. And a 0 in all the other columns. You can even remove one of them because it's given by the other 2. If you only have 3 possible values, and you know that these 2 are 0, then this must be a 1. And the same is true, of course, for all the others. If you know that this is a 1, well, you don't need this anymore. If you know this is a 1, you don't need this anymore. These 2 encode sufficiently enough information. This is called one-hot encoding or dummy variables. But it's not the same for all algorithms. So for linear regression, you would do this and remove this. It's kind of what I said before. If variables are highly correlated, you don't need to include them all. And here you have a perfect correlation. Of course, it's a perfect correlation between 2 variables and this one. So you don't need this. For other algorithms, SVM, which we are not covering in this lecture, you would use all 3 variables. If you have some time at home, try to find out why that is. Often you as a human understand quite well what the variables are about. If you see gender, you know what to expect. If you see square meters, you know what that means. If you see price, you know what that means. Sometimes features have no inherent meaning to you and also probably not to a machine learning algorithm. There's one, the Titanic data set. Now here it's also another popular machine learning data set. It's a data set that lets you predict if a person will survive the Titanic or not. And it's giving you a lot of features such as passenger idea. Well, then if the passenger survived or not, which class the passenger was traveling, gender, age, some other things, ticket number, fare, and the cabin. And the cabin number itself is kind of meaningless. It's just some strings. But if you would look at the map of the Titanic and then you see where the cabins are located, and you could say, oh, it's the upper deck, the lower deck, it's in the front, in the middle, in the back, that would provide much more valuable information to the machine learning model as well, because I don't know exactly, but I mean, the Titanic crashed on an iceberg, right? So probably the people in front, I don't know, were less likely to survive because there was water faster, and then also that part sunk first. I assume, maybe it's the other way around. But either way, the location or at the lower decks, people probably died more often because there was the water first. So the information where your cabin is located would be a strong predictor for survival chance. So it can make sense as a machine learning engineer to look at your features and think, oh, here I can help the machine learning model. And then you maybe take some external data, like the map of the Titanic, and convert that somehow. Or the other way around, GPS data. Unless you have a model that is specifically trained to understand geometry and the world, the GPS coordinates are quite meaningless. It's just a long decimal number. You probably know this, right? A GPS coordinate, it's 2 numbers. And it tells you very precisely where on Earth this point is located. But it's not so meaningful if you convert this into country and city, for instance. Chances are high your machine learning model will learn better. But then again, if you convert it to city and country, you should probably convert it to this. And you see again, of course, the data becomes much bigger at the table. Think about this, we talked already. Scaling features. It's important that if you have features with different scale, and you always have features with different scales, that you scale them so that they are comparable. We had that with our, I think, the student, the salary example, that if you plot the salary, which is a very large number, versus hours spent or average marks versus hours spent, you have a different scale. The marks the students achieve range from 1 to 5, and the hours spent per week range from 0 to 20 or 40, something like this. And if you then, so this example is age and salary. If you then use something like Euclidean distance, then the features have a different weight. Yeah, if you wanted to build some groups here, it would look like this. And the features with a larger scale impact much more the distance. Or if you then have like an outlier, someone with an extremely high salary, like here, then this would look like this. So basically, it appears to be all the same almost. There's different solutions to this. Simple methods include just taking the square root or the logarithm or the square. That's the opposite effect. But that's normally not really good because you have to really look at all the data and decide what to choose, and then you still have differences in scaling. So normally what you should do, and what you should also learn for the exam, is this one and this one. The min-max normalization, which is scaling your values to a number between 0 and 1. And standardization, which is scaling your values to a normal distribution. That's what we just said before, Z-score normalization. You remember Z-score, it's like basically the number of standard deviations. So you are scaling your data in a way, let's talk about this one first. Min-max normalization is very simple. You take the value that you have, that you want to normalize, you subtract the minimum value and you divide it by max minus min. That gives you, if you think of, let's say you have the minimum value. So let's say you currently want to normalize the value that is smallest, then this would be 0. And this would also be 0. So the output is, well, it's not defined, but so by definition, it's 0. If you have the largest value, you will have 1. Slightly more complex is then the standardization, Z-score normalization, where you take x minus the average divided by the standard deviation. What I just said was wrong, right here, up here. X should also be the, what's x? Let's look at the next slide. There's an example. Oh, I have my calculations not here. Anyway, you can look at that at home and figure that out yourself. If you have this data given, similar to the examples that we used before, you have the min, the max, the mean, and the standard deviation for those 2 columns. Then this is giving you the data for the normalized min-max, and that is giving you the standardized Z-score. I will take a note. I must put that clearer on the slides. So this is giving you values between 0 and 1, and here the same 0 and 1. The Z-score normalization has no given or maximum or minimum. It's like normalized around the mean. So we have a break or continue? When did we start? 8:30. It's not so many slides. I think we just go through this and then we finish. Sometimes it makes sense to merge features. And one good example is if you want to calculate, or if you have information like the length and the width of a site, of some in German Grundstück, of an apartment. Because what determines the price of some site or an apartment is the square meters typically. So if the square meters are not given, but you only have the length and the width, you can support the machine learning model by calculating square meters yourself. Just multiply length and width, or do that for all the rooms. Or maybe if you have the square meters given for each individual room, just sum up all the square meters to give the total square meter size. A good machine learning model would be able at some point after some time to probably identify that the larger all these individual rooms are altogether, the higher the price. But if you provide the total square meters directly, the machine learning model likely could save some iterations. So that's just one, and there's no guidelines on when and how to do that. This is just then like practice and experience that you see this and you think, I could support the machine learning model maybe by calculating a new feature. And then you try it and you see it works or it doesn't work. So you can try it automatically by just taking all feature combinations and multiply them, subtract them, take the power, take the sum. But that takes, of course, then again, much more computational power. And once you calculated all these features, like before, you should do feature selection. And like I taught you, there's not the one feature selection methods, there's different methods that is computationally expensive as well. So this is really exponentially increasing. The more you do, the more time, the much more time this will take. We are not talking so much about images in this lecture series, but here's one example. Imagine you want to do image classification. For image classification, you need many, many images typically of one class. So if you want to classify images, that it's, what animal is this? Wombat? No, I don't think so. It's not a mouse, it's not a rat, it's a hamster. So it's an animal. And imagine you want to classify many animals. You need many images of them, but you only have, let's assume, 1 or 2. You think about what you could do to easily increase the number of images. And meanwhile, I asked ChatGPT what this image is showing. Yeah, let's assume you have one image or a few images of each animal, and you need much more. And I'm not talking about, you can of course go to some digital library and find more images, but you want to work with the images you have. Give me 1 minute, I must ask ChatGPT first, you can use the time to think. It's a quokka, ChatGPT says. Lives in Western Australia. Okay, you raised your hand. You had an idea. Yes. Yeah. 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 Exactly. So you take an existing image and just change it in many, many ways. You can rotate it, you can change the size, you can change the brightness, just whatever you said and everything else. So out of one image, you could potentially easily create 100 images or more if you want, if you have the resources to use all of that for your training. This is also called, or you can it's called dataset augmentation. Sorry. Yeah. We go now one step back about prepare. Yeah. Yes. Okay, for those online, the question of the student was if an image like this, and probably also like this, makes the training really better. I'm not working with images in machine learning, so I cannot really tell you from my practical experience. I never tried that. But in general, I mean, of course, there will never be an animal or a photo looking like this, but it still potentially can make the model more robust because it's still showing this animal, right? So the assumption probably is if the model learns to identify this animal from this kind of weird picture, there may be other weird pictures for real of this animal that can be identified correctly then.
But now that we also like you have a picture from the sun which maybe looks similar to this, would they classify that?
So probably you would have an image like this actually for each of your animals. Yeah, if you augment each image of each animal, you would always have the same routine. So for each, so let's say if this is the original image, then for each other image, you would have a rotation like this. You would have like mirroring and blurring it like this, and you would have this. So, and in a data set for animals, you would not have a picture only of the sun, probably. But if you want to have a multi-purpose image classification model, yes, but then maybe you also would have many pictures of the sun. And you would see, and the model could learn that this is an animal and the sun is the sun. Why is this all the time here? Good. Let's go one step back and talk about a few more practical things like how to get data. As a student, you're in the lucky situation that in the lab session, my assistant Tabea will tell you, here are the data sets, please use that. If you do a bachelor thesis or a master thesis, you are probably in the lucky situation that your professor tells you, here's the data set, or your company. Or at least they will tell you, look, here's a website with a list of long data sets, pick a few that are good for you. But then one day you will work in a company and very likely the company is not willing to pay your salary so that you increase the performance on some external data sets with a machine learning algorithm, but they give you their own data. And if you're lucky, the company has this data already, and then everything is perfect. Job done. But chances are high that you don't have all the data that you need in a machine learning environment. So maybe you want to play around first with some data sets to see if your idea is working, or you have some data in the company and you want to augment the data with additional information. For instance, let's say you have information about your customers, where they live, their names, whatever, but especially let's say their address. You could look for external data sources that tells you more information about your customers based on the address. Based on the address of a person, you can estimate their income, their education, and many things more. Now, many companies do that. They buy information like census data, if they are religious, or I don't know, there's surprisingly a lot of information. Even if you do a bachelor thesis and you don't have a data set from your professor, good starting points are Google, which has their own data set search. And Kaggle is also a good starting point. And there's many, many websites more. We are not talking now about all of them. You can just look at the slides if you do your bachelor thesis or something. Amazon has a large number of data sets. There's a small problem about the Amazon data sets. They change them. And I believe they are not really making clear how they change it. So if you do some experiments, everything is fine. Then a year later, someone else wants to repeat your experiments and they download the data set from Amazon. The data set will be different from the data set that you used for your experiments. That's not really ideal. And nobody knows what has changed. Movie Lens, that's like a standard data set for recommendations. That's a data set that I released. That's the data set actually about the recommendations as a service with these redundant clicks and bots that were crawling the recommendations. So we released this, I think, 4 years ago, or probably longer already. So it includes 57 million delivered recommendations. We recommended 2 million documents, so it's pretty large, and it contains 77,000 clicks, a relatively small number compared to the very large number of delivered recommendations. And much, much more. If you have a really novel idea for some application based on machine learning, chances are high that you have to create your own data. It's just not there. One example, or maybe some part of the data is there, but not the labels, not what you want to predict. Before after I did my PhD and before I decided to go to academia, I worked for HRS, a hotel reservation website. Some of you may know this. It's similar like booking.com. And what we wanted to do is to predict which image we should display as the main image to customers. So we wanted the machine learning model that looks at all the images and then says, this will be the most appealing image to customers. Or this is the most beautiful image. So what we did is we hired students, and they were sitting there the whole time looking at images and saying, that's the best. Or I don't remember if they said that's the best, or if they just gave numbers and said, okay, out of 10, this is an 8, and this is a 5. And we used that data to train the images. There's one problem about this. This was shortly before I left, so I don't remember how well this worked. But if you are a company and you would have the same problem, you want to know how attractive images for hotels were, or actually more precisely, we did that for vacation rentals, so like on Airbnb, where you rent apartments or rooms in private homes. Is it a good idea to hire students and then they rate the images? Yeah. Yeah. I mean, that's absolutely right. Students are maybe not the right demographic group to judge which images are good for people who book a hotel room like this. I mean, who of you ever has booked a hotel room that looks like this and costs 180 euros per night? Is it per night? Yes. Oh, no, it's dollars, so 160 euros per night. Who of you has ever done that? I thought so. So but other people do that. So it's difficult, of course, but the other problem is you cannot hire someone to rate images. If you cannot hire a person that is willing to pay 160 euros per night for a hotel to rate images. A person who can pay 160 euros for a hotel will not work for you for 10 or 15 euros per hour and sit there the whole time and say, good image, bad image, bad image. So you must do a compromise somehow. And I mean, this is quite a boring job, right? To rate images. Or I once was approached by a company, also why, I mean, this is standard now, but at that time it was quite novel. They wanted an app for a mobile phone that can digitalize receipts. So you take a photo of a receipt and then you get this. So on the one hand, you need to recognize this is the receipt. That's not so difficult. But much more importantly, identify. So if you are a business and your employees buy something, then they could use this app, or if you have your own business, and put this into your accounting system. To do that, it's important that you know the name of the business where you bought something, maybe the items that you bought, and definitely the full price that you paid and the tax or the tip that you gave. You cannot just feed this into machine learning. You need the labels. So you need people who say that's the name of the company. That is the total sum that someone paid. And I think I mentioned in one of the first lectures, you can use human labor like we did for the images. And it's a big business. Companies like Google are doing this, labeling as a service. So what are the costs? So if you want to classify, so they have human persons doing this. Google has a large workforce doing this. And if you want to classify 1,000 images, you pay $35. If you want a bounding box would be like a rectangle around a car. You have an image of traffic, and maybe you want to say, okay, I want to identify the car or the traffic light. Then a human would make a rectangle and say, here, there's a car. Segmentation would probably refer to an image where you have many bounding boxes and say, here's a car, there's a traffic light, there's a pedestrian, something like this. And that becomes already much more expensive, $870 for 1,000 images. Mechanical Turk, I introduced that before, that's the same. You create a task and then a human is doing that task. There's one big problem with these things. If you go to a website like Amazon Mechanical Turk, there's some anonymous people sitting all over the world getting, I don't know, 10 cents to classify an image. What would you do if you were one of these people? Someone tells you, you must tell me for these 1,000 images if it's a good image or not. And it would take you, if you do this thoroughly, maybe, let's say, 10 seconds per image. But you don't have a lot of money, but you want a lot of money. So what would you do? You would just click, 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 right? 1 second, one image. That happens a lot. And I mean, that's a simple task, but also there's more complex tasks on Mechanical Turk where maybe you show where the person should read 2 texts and then say which one is better. So that would take the person, if they do it thoroughly, 5 minutes, 10 minutes. But let's say, so if you really ever use this to create data for machine learning, you must think of some mechanisms how you can detect people who are not doing a good job. So think about this. Imagine you ask those people, look at this image, what would be a good recommendation? Would this be a good recommendation or this be a good recommendation? How could you design this experiment in a way that you can identify people who are malicious and not serious about this? Yeah. Yeah. Introduce some, it's like something to catch them. If a user ever, if one of the employees ever chooses this, then obviously it was maybe a bot or someone who's really not looking at the images at all. And then you could filter all the responses. New question. How much data do we need for machine? Any questions so far? How much data do we need? Yeah. Oh, absolutely. So you know that you need completely new data if the existing tools are not good enough. So you try, of course, you try out the state of the art, you try out existing software libraries, and if you then find it's not good enough, then you hire some people. And of course, with the recent developments, machine learning is already so good that for many use cases, you can use AI to create data. And this is also, let me go one step back. For a long time, machine learning was the more data you have, the better. So companies try to get more and more data and maybe find ways of processing that quickly enough. And now we are at a point where tools like ChatGPT, large language models, are trained on basically all data that exists in the world. Almost like the entire internet, large amounts of books from libraries, and then like YouTube, like Google is using YouTube videos for the training. So it's gigantic. It's almost all the data that exists. So that's a problem now because we cannot get more data to improve the training. So as a consequence, these companies now think about alternative solutions, how with the existing data they can get out more of it. It's a very interesting research field. One way is like, it's called curriculum learning. So similar like in a school or at the university. Right now, you just put all the data in. There's no order, but with curriculum learning, you would order your data for specific tasks and start with simple tasks. Like, let's say you want to predict house prices, very simple. You would maybe start with, no, that's not a good example. Anyway, you sort your data based on how difficult it is to learn. And that's just one of many ideas. I lost a little bit track, sorry. And then, yeah, right. So, and the other way is that you use AI to generate more data. So many companies do that now, like OpenAI, all the big AI companies do that. They use AI to generate more data and use that data to improve their models even further. Of course, there's some limits to it because, well, of course, there's still a difference between human data and AI-generated data, but it works to some extent. So most of you don't need to worry about that so much. If you work in a normal company, you will just have a few thousand customers, maybe tens of thousands of customers. So relatively small data sets, but even then you need to think about how much data do you really need to train your models. And this is just one example. And you see, there's never like the definite answer. That's why I show you so many examples, because I cannot show you a generic theory about how much data you need. What you see here is the number of training instances ranging from, well, a few hundred up to a few thousand. And then you see the accuracy. I don't know which algorithm that is, but that's also not important. So there are 19 features. And you see in the beginning, the accuracy increases. And here that's the band of the results. So they repeated their results also multiple times. And you see that the accuracy increases. You could say continuously, always a little bit, but in this part, it's almost stable. So I took that chart from some textbook from this one here. And this textbook says the accuracy increases until here. I would kind of disagree. I would rather say you need like this much data or possibly even this much data. But that also depends on your interpretation and how good you really need to be. Because of course, training with 500 instances maybe is, or 1000 is much faster than training with this. But you can see that the more data, the better, at least until a certain point. So have a look at this slide. That's a study some years ago where researchers looked at 4 algorithms. So be careful, that's a logarithmic scale here. Millions of words for training and the accuracy. And they argued that companies should not spend so much time in improving the algorithms, because you see the algorithms are relatively close together, but they should spend more time in getting good data, because you can see that the more data, the higher the accuracy. So they said, these results suggest that we may want to reconsider the trade-off between spending time and money on algorithm development versus spending it on corpus development. So, did you answer this already? Or is it from last year? Did you answer this already? Can you raise your hand if you... Did I probably actually forgot. I think I also forgot to update this slide. Do you see this now in your... Anyway, I think we skipped the Menti. You just look at this, look at the results, and think about how much data would you use for training if you had the computational resources and you don't care so much about costs. You can put your phones down. Just look at this and we talk about it. Would you use like as much data as possible? Or is this already good enough? Or this much, like 10 millions? Yeah. I mean, still money plays a little bit of, but yeah, it was almost for free, but okay, let's say for free. Because it always increases the performance.
Always increases.
I mean,
we started it not always increasing before. At some point, and that's what I meant with some point the threshold very stable, I guess.
Yeah.
So this would be then also fine, but if it's completely why not?
Yeah, okay. I mean, you can probably see, or this kind of saturates. You could assume that this kind of continues like this. I mean, it will not go like here. It rather will be like this. So you would use 1,000 million, or even, yeah, 1,000 million, so 1 billion words, right? Any other opinions?
Also use 100.
Yeah, 100 million. Okay. So one important thing is, again, always, if you have a logarithmic axis, think about how this would look if it's not logarithmic. And that's what I just plotted here. If you plot that in a, let's say, a normal scale, the chart would look like this. And here I would argue, of course, if training really was completely for free, and if you have unlimited time, of course, you could use as much data as possible. But if you look at this chart, I believe the conclusion differs from here. I would argue, if I look at this chart, algorithmic development makes sense. I mean, the blue algorithm clearly is much worse than the other ones. And once you are here, let's say roughly around 100 million, training, like the performance improves really marginally. So this is less about how much data you need, but again more about critical thinking and chart analysis. I do this all the time a little bit in this lecture series because I think it's a really important skill, not just as a machine learning engineer, but as a good citizen to understand statistics. Yeah.
One question, like does like the more data mean it's also more robust if accuracy stays the same? Because otherwise it wouldn't really make sense to have more data less the accuracy. With accuracy set rates, it wouldn't make sense to have more data. But in the example before, you like intentionally like when several centimeters are right of the saturation point due to robustness, or
no. No, it's not getting more robust if you have more data. Once the accuracy, I mean, what you can always do is really look at the training curve. So looking at one. So I mean, each point here is one full training, right? You do the entire training and evaluation with 100 million words. Then you start a completely new experiment and you have a new result for 101 million and for 1000 million. You could look, and that's a good thing to do in general, look at the training curve. So look at one single run. And if you see, I mean, we had that before. If your results, if your training error looks like this, that's maybe not perfect. You would rather have something like, I mean, in the beginning, you always have some, you want it relatively stable maybe. And this is also, I'm not sure if I have a slide for that. I once had a student, he was doing a very interesting project, like quite a complex algorithm, and his results appeared good. I remember the first time he showed me his results, I thought, okay, for the first time, really, really good. But then later we looked at the training curve and it was really just like this. And not just the training curve, also the validation and test. So what that means is the model is not learning anything. The overall result was good, the predictions. But we found out that in the end, the model always predicted the average of a number. So we wanted to predict some numbers and the model always predicted the overall average. And that was still a reasonable good guess. But it was, I mean, not what we wanted, of course. If your machine learning model just learns to predict basically and output almost always the same number, I mean, you don't need a machine learning model for that. Okay, what can go wrong even if there's a lot? Yeah. Yeah.
from my understanding, outliers also takes into account like the accuracy. Right?
Yeah, it's okay. The term robustness is not really used in this context. What you refer to is probably bias and variance, what we had, I think, last lecture. And the term generalizability is important. So what you want to achieve is that your model that you have after the training predicts well new unknown data. And if it's doing that well, you would say it generalizes well. And you can say that like a model that is simple, that has a low degree of freedom, it's robust against outliers, for instance. Or there's also some, like there's differences between different algorithms, between random forests and linear regression, how robust they are, for instance, to outliers. But that then has nothing really to do with this. And the term robustness is used in many different contexts in machine learning.
Robustness against say linear regression with both the freedom robustness
Yeah. I actually don't know how that is measured. I've never really thought of that in detail. I'm sure there are some colleagues who spend a lot of time thinking about this. But I'm very sure that there will be metrics on how to measure robustness. But in the same way as for outliers, it's not a natural law. Just someone will have defined some metrics and people thought, okay, that sounds plausible. There's lots of things that can go wrong, even if you have lots of data. First thing is kind of what we had with the falling cats, that the data is just not representative. You can have lots of data, but if it's not from the people or the products or the items you want to make predictions for in the future, it's kind of meaningless. And that can happen often. If you, let me think, if you want to make predictions in health care, maybe if a person has cancer or what treatment to do, and you have data that is very old, maybe you have collected medical data over the past 30 years, then there's a good chance that the data from 30 years ago is not very representative anymore for today's medical advancements. If you measured 30 years ago, maybe the heart rate or what medication someone got, then nowadays, maybe heart rate or some ultrasonic pictures would be much more precise and maybe medication would differ. So you must think of that and be careful. Think of the falling cats examples. Yeah, that was what I just mentioned. There's many reasons why data is not representative. It can be outdated data. It can be a sampling error. I'm not sure if I have a slide on that, but a very bad practice, in my opinion, is that many machine learning engineers, and also in my field of research with recommender systems, many researchers remove some part of the data that doesn't really suit their purpose. So in recommender systems, there's algorithms that need ratings from users. So basically, if my algorithm wants to make a prediction what item you like, and this algorithm must know how many stars you gave to previous items or movies you watched. And of course, so that this algorithm can give you a recommendation, you must have rated items in the past. And typically, the more items you have rated, the better this algorithm can give you a recommendation. That's probably not a surprise. And many researchers then just remove all users with less than 5 or 10 or 20 ratings from the data set, because they say, my algorithm needs ratings, so I just ignore all the users who have very few ratings. And in some cases, that leads to removing like 10, 20, 30, or even 50% of all the users from the data set. And if you then say, look, I have an algorithm, it works really well, that's not the full picture, because then the researcher should say, it works really well for half of my users. But they don't do that. And frankly, how useful is an algorithm that works well for 50% or even less of your users? I would argue the usefulness is very limited. You want an algorithm that works well for pretty much all your users. Or, of course, it's still good to have an algorithm that makes half your users happy, but what about the other half? You should also at least think about that and mention that in your bachelor thesis or in your research paper. Data leakage, again, I have no points on here, so I explain that just to you in my own words. That's a really nasty one. Data leakage means that some of your labels that you want to predict are somehow included in the training data. But you will not have this information in the future for known and for new data. And this will completely spoil your experiments. If you somehow include your labels in the training data, of course, your algorithm will be very good. But then you don't have this data in the future. Can you think of any example where that could happen? Yeah. Yeah, that's a good example. Maybe I even have a slide on that later. If you do time series prediction, so let's say that's a time series, you want to predict that. And then there's two ways of doing that. You could either remove this, and this data point and make a prediction. That's super easy, right? I mean, of course, a machine learning model can very easily learn where, if you want to make a prediction for here, where the value is, because the model knows this and this value, and here the same. Or the alternative would be you remove all of this data. That would be much more difficult. This is not really an example of data leakage, but it's very closely related. So one example would be what I just explained to you before, that you should calculate new features. I told you often it's useful to calculate new features. And again, thinking of recommendations where you maybe want to predict how much stars a user gave to an item. And then I explained to you sometimes it's maybe helpful to help the machine learning model by calculating new features. And what I did many years ago, and some of my students, we thought, okay, it would be good to know what the average rating of a user is. How many stars does a user give on average to an item? Because some users are always very critical, or like what's the minimum rating and the maximum rating? Because some users are very critical and other users like always give 5 stars. So we introduced a new feature, a new column, and calculated the average rating. But the problem is we calculated this average rating on all ratings a user made. So that means, to give you just a very simple example, let's say a user made 10 ratings in total in the whole data set. We calculated the average, and then we remove 1 rating later for the testing. That would be super easy for the machine learning model to give a perfect prediction. If you know the overall average and then you have 9 of 10 values, you can calculate precisely the missing value. And this is really something that, camera off again. This is really something that happened to us, but that can happen very easily and that you see happening quite often. Or if you just have 2 really strongly dependent variables. I don't have a really good example, but let's say you want to predict the age and you have the birth year in your feature list. I mean, that's obvious then how then the machine learning model will perform very well. It's not really a good example because why would you have the birth year and the age and then later you want to predict the age but don't have the birth year? But I hope you get the point. So when you calculate new features, be very careful about data leakage, that you don't include anything that is based on the labels. It still would make sense to calculate, and we did that, it still makes sense to calculate the average rating of a user, but you must only use the ratings that are in your training data set, not in your entire data set. So I show you many examples, like from my own work, to also show to you that this can happen to everyone, and it's really difficult to sometimes find this. If you look at this, is there anything strange to you? If you would have this as an output for your bachelor thesis, would you think, I should look deeper into this? So we just wanted to analyze how the data is distributed. So we had one of these data sets that contained how users are rating movies, and we wanted to see how many movies do the users rate on average. And we had this distribution. So 16% of all users rated 1 to 9 movies. 26% of all users rated 10 to 19 movies, and so on. here you have this little jump, but that's only because we changed the bin size. You see here it's always 10, the difference of 10, 10, 10, and here it's different of 50. Anything, or if you are a professor and a student comes to you with this, would you say, oh, there's something that is weird? We should look deeper into that. Yeah. What about users with 0 ratings? Okay, good question, but the answer is simple and correct. There are just no users with 0 ratings included. Yeah, that's a good question, but that's not what there's something much more. So this was, yeah. Yeah, that is strange. That is strange. That would be something maybe we could try to find out. Yeah, but I have something else. So the orange data is summarized in bins, and I mean that's very normal for a bar chart that you make bins. But we then had a look at every single number. So how many users had 1 rating? How many users had 2 ratings? How many users had 3 ratings, 4, 5, 6? And we found this pattern up to 20. And I would say that is very weird. Why do you have this zigzag from high to low, and I mean really constant, from high to low, high, low, extremely high? Now, if you look at this, and up to now, I still don't know why that is. I mean, that's the real data. That's how it is in the data set. But it would be very interesting to know why the people who created this data set or how they collected the data. And this was pure chance that the student later did this analysis. I mean, yeah, normally, if you do data visualization, you would just do this. It's absolutely fine. There's nothing to criticize about that. But for some reason, the student later also did this. And yeah, very weird. And this is really, there's no trick I can tell you how you find this. This is just things that will happen and that you need to keep in mind. And maybe that you, over time, will learn to analyze. So I now always tell my students, don't bin your data, but look at every single point. Yeah, I mentioned this many times, but really visualize the data, try to understand your data. How does it look like? Get ideas, what features to use, get ideas. So this is scatter plots. How is your data distributed? You can just sometimes make clicks and then you have a good idea what to do with your data. Bar charts, obviously. Mosaic plots. I don't like them so much. It's a bit difficult to understand, I feel. But yeah, have a look at that yourself later. Boxplot, I explained to you already. Yeah, that's a decision help. This is not relevant for the exam. Just giving you some indication when to use which plot. But I think once you used different plots a few times, you just have a feeling about what is useful when. Coming back to critical thinking. Let's look at a few more charts. This is a chart that was really published on a website or on some report. Planned Parenthood. Who of you knows Planned Parenthood in America? It's an organization that I believe is critical about. No, wait a second. Planned Parenthood is an organization that is like giving advice to women, doing medical, like advice also about abortion, doing medical exams. And then there's some other organization, Americans United for Life. So a group that is rather critical when it comes to abortion. And they published this. Have a look at that first. What is it showing? Well, don't look too long at it. just look at the first impression. What is this chart telling us? Yeah. Yep. Oh, okay, then say something different. Yeah, so you are one step ahead. If you look at this chart, it tells you the number of cancer screening and prevention service goes down a lot, and pretty much in the same amount, the number of abortions goes up. Now, if you look at the real data being published, it looks like this. So indeed, the number of cancer screenings goes down notably, and that is, I don't know, that's probably something people should ask, why is that? But the number of abortions stays pretty constant. It goes slightly up, but clearly not like this. So this is, and you see, I mean, you see things like this everywhere. Also in, I mean, you could now argue, oh, this is probably just some small, unimportant organization. I don't know. But you also see things like this in newspapers. And if you even then look at all the services that Planned Parenthood is offering, you see that other things like STD, so that's like diseases of the genitals, goes up, and yeah, many other things remain stable. And abortion and cancer screening are just 2 out of many services. So this is actually the original chart published by Planned Parenthood. So this is called cherry picking. If out of the full data, you use only some selected. You have probably heard of correlation and causality, and that one does not necessarily impact the other one. It is really true that there's a high correlation, at least in some areas, between margarine consumption and divorce rate. That means people who eat a lot of margarine have a much higher chance of getting divorced. Or, I mean, that's again like a real news article. Fast food can make you depressed and unable to control your emotions, new study suggests, because there was a high correlation between fast food consumption and depression. But does that really mean that fast food is causing depression? No, it's not. It could be exactly the other way around as well. It could be that people with depressions just eat more fast food. Or, like here, that it's just a coincidence. I mean, this has nothing to do with each other. There's a third factor. There must be a third factor that influences both. I don't know what that could be. So here it could be this way, but you could also turn around the chart as well. The good thing for machine learning, why do I show this to you, is for machine learning, it doesn't matter if there's causality or not. For machine learning, correlation is very important. So if you want to predict if a couple gets divorced and you know their intake of margarine, that's fine. I mean, clearly the margarine will not cause the divorce, but it's a good predictor. So you can use that for training your machine learning model. Same about fast food and depression. It doesn't matter which one is causing what. If you want to predict if a person has depression and you know the person eats a lot of fast food, it's a good predictor, and the other way around, and that's fine. Good, I think that concludes the lecture again for today. There's just many, many more. I go through this very quickly. If you want to learn more about machine learning, if you want to look for competitions where you can apply what you have learned here in your spare time, go to these websites. TechCrunch is a good news website, not just about machine learning, but about tech and IT, Google AI blog, many, many more. Yeah. This is really just for a lookup. We don't need to talk about that. Many libraries. Yeah, that's interesting. That's an old chart. So actually, when I started to give this lecture at that time, okay, TensorFlow became very popular, but you see that scikit-learn was still just slightly ahead of some other libraries. And you have probably never heard of any of these libraries, I assume. Because nowadays, scikit-learn is probably here, along with TensorFlow. Same with Python. When I started this lecture series, there was big discussion, Python or R. Who of you knows R? A few. So it's similar like Python, but just much more ugly, I believe. Like the syntax, at least. It's not as intuitive. And at that time, still more or less the same. I'm pretty sure today Python is here and R is down here somewhere. Yeah. Okay. Let me quickly go through this. Yeah. Any more questions? If not, thank you very much and see you, I think, next week already, right? Yeah. Good. Thank you.